Okay. Welcome to this session, which has the title Analysis of Radionuclide Monitoring Data. So, I work at the Swedish NDC, and when we get radionuclide data, what do we do with them? Well, you want to locate the source, you want to calculate, if you can, the released amount, you want to look at isotopic ratios and compare with hypothetical scenarios. And this is very, very briefly what you do. And this session will talk a lot about that in different ways. And I think it's really crucial and interesting. And we have a nice collection of talks here today. So we have the presenters here. I think Miley should also present. He will maybe come later. We first have Don Lucas, and then we have Ian Hoffman sitting here, and we have Miley as well coming later, and we have Pieter de Meutter and Emily Gordon who will talk different aspects of this problem. So I think we have 15 minutes for each talk, and we hopefully can squeeze a couple of questions in between. But then maybe also at the end, if we have some time, we could also take some more questions if we have time. All right? Okay. So we just start right away with Don Lucas talking about machine learning enhanced detection of radionuclide anomalies. Please.
Hello. All right. So I'll wait for my slides to show up. But yeah, essentially, while I'm waiting, it's an honor to kick off this session, and I'm excited to hear everybody's presentation. I will be talking about using machine learning algorithms to help identify anomalies in radionuclide data. And I think we got to wait until the time before it gets queued up. A joke, yeah. The joke is you're presenting Harry's presentation. All right, so we're good to go? All right, so I basically want to introduce you to how machine learning can be helpful for identifying anomalies in radionuclide data. And where do I point? I cannot, oops, go back. There we go. All right, so this is about anomalies and anomaly detection, and there's no general definition about what an anomaly is, but loosely speaking, an anomaly is an outlier, or it's a data point or set of data points that lie far from other data points or a distribution of data points in a multi-dimensional data set. And anomalies occur in many, many different fields. And so what we want to do is borrow algorithms that were developed in these other fields and see if they can be useful for identifying anomalies, nuclear explosion signals, in radionuclide data. So in the financial industry, anomaly detection algorithms are used to try to identify fraudulent activity on credit card transactions. Anomalies are used in cybersecurity to try to identify computer intruders in computer systems. Anomaly detection is used in the healthcare industry to help identify diseases and so on. So for this audience, in this context, what we're interested in is applying these algorithms to see if it can help us identify a nuclear explosion signal in the sea of background radionuclides that are present in the atmosphere. And why is it complicated in the atmosphere? Oops, let me go back one. There's a little movie. One more. It's on autoplay. Can you play the movie? So what this is showing is illustrating the complexity of trying to identify anomalies in Xenon 133. So this is releasing Xenon from about 200 locations around the world on January 1st, 2019, using realistic weather, and advecting and transporting those separate plumes for 3 days. And it doesn't take long for you to realize that everything mixes together, and if you're trying to hide a nuclear signal in this sea of background, it can be very challenging to identify that type of anomaly. So this is a challenging problem for RN data. So what does the IDC do for identifying anomalies? So I'm presenting here a time series of Xenon 133 at the USX 75 station in Charlottesville, Virginia. This is the set of data for 2014. And you see some anomalies that are identified by the IDC's algorithm, color-coded in red, and there's a line there called the abnormal threshold, and that's used to delineate what is an anomaly. And so what is the abnormal threshold, and how is it calculated? So what you can do is you take that time series of data and you bin it up and create a histogram, and once you have a histogram, you can convert it into a cumulative distribution function, or CDF, and you can extract quantiles from the CDF. And so the abnormal threshold is defined as collections that are above the median value plus 3 times the interquartile distance, or range. And so if the value is above there, it's deemed to be an anomaly. And for the data that I just showed you, it corresponds to a value of about 6.1 millibecquerel per meter cubed. Now, a couple of things to keep in mind. So this is an easy algorithm to run, simple formula, but it's applied to a single isotope, not pairs of isotopes, not collections from different stations, and it doesn't consider atmospheric models like the movie I just showed you. And so what do you want to do, or what can you do if you want to fold in additional information? Well, it becomes challenging if you're trying to compute quantiles in higher dimensional data sets. So what I was showing you before was a one-dimensional time series. It's easy to compute a quantile. It's a zero-dimensional point in a one-dimensional data set, and you can assign that value very easily. If you have a two-dimensional data set, what you need to do is find a contour or a line in that 2D space. And on one side of the line, you would call that an anomaly. On the other side, you would not. And it becomes harder to actually calculate that contour in two-dimensional space. So what do you do if you have three-dimensional data? Well, essentially what you're doing is trying to map out a two-dimensional surface in a three-dimensional space. And that becomes a very challenging problem to estimate those quantiles. And IMS data is inherently multi-dimensional. Well, this is where machine learning can come in and help us calculate these outliers or anomalies, hopefully a little bit easier. So I introduced earlier in the talk some of the different communities that use and apply anomaly detection algorithms. What that means is there are packages that are available and out there and easy to use to apply these anomaly detection algorithms. So I have a couple of screenshots of a couple of standard packages. sklearn has novelty and outlier detection. And then the PyOD library has about 40 different flavors of anomaly detection that are really easy to use. So I'm going to spend the rest of the talk illustrating one algorithm and some results from that algorithm. And so this algorithm, it's called an isolation forest. It's included in both of those Python packages that I just introduced. And it's an unsupervised machine learning algorithm, and it's essentially a randomized decision tree. And I'm showing two little movies of applying an isolation forest to identify an inlier point on the left-hand side and an outlier point on the right-hand side. So the anomaly in this case would be the outlier point. And so the decision tree, one way to measure how if a given point is an inlier or outlier is how deep the tree must be before you can isolate that point. So on the left-hand side, for the inlier point, the tree has to have a depth of 22. It's pretty deep. It takes a lot of partitioning before it can isolate that point, whereas the outlier point on the right-hand side requires a less deep tree, and then it can isolate that point. So there's a relationship between the depth of a random forest, isolation forest, and a quantile number. So we can leverage that, and just note that these are two-dimensional data sets. These algorithms work just as easily in three-dimensional, four-dimensional, and higher dimensional data sets. So thinking back to the time series that I presented earlier, it was Xenon 133, all of the collections in 2014 at Charlottesville. So it's difficult to apply and compute quantiles for pairs of isotopes, but you can do that with isolation forest. So this is showing Xenon 133 and 131M put through an isolation forest and trying to identify the anomalous points. And what we see is that the two isotopes are fairly well correlated, which is kind of expected, and that the algorithm is able to automatically label what would be considered an inlier and outlier point. And the heat map in the background is a quantitative measure that comes out of the algorithm. So that would be analogous to a quantile statistic. So you can calibrate the output of these machine learning models to give you information that would be analogous to quantiles. So you don't only need to consider just different isotopes. You can also inject ATM results. And if you have an ATM model, as long as you're getting the transport and the emissions right, then we would expect to see a correlation between the ATM, atmospheric transport model, and the variations that are measured at an IMS station. So I'm showing you an example here. That, again, this is Xenon 133 measured in 2014 on the top at USX 75. And then there are two ATM simulations shown below. And I won't go into the details on how those simulations were constructed here, but one of them is using a prior distribution and then doing some adjustment on the emissions to improve the fit. And so what you can do is take the ATM output and input that into the isolation force to help identify anomalies. So I'm taking the black time series, which is measurements, and the red time series, which is the model simulation. You can put that into an isolation forest, and you get out a set of information related to what would be considered an anomaly and what would be considered an inlier point. And again, you get a heat map with quantitative information about how far those points are from sort of the centroid, or how much of an outlier or inlier they may be. You could potentially start to bring in information from different stations. So I'm showing here now, putting in Xenon 133 measurements measured at RN 74 in Kansas, which is somewhat close to RN 75 in Virginia. So these are binned by time and then put through the isolation forest. And we see that the algorithm successfully identifies inliers and outliers, but the data is not strongly correlated. That's because those two IMS stations are seeing different weather and different emission patterns and things of that nature. So we wouldn't expect to see a strong correlation, but this is where the ATM, or atmospheric transport model, can come in to help sort of correlate what would be expected at the two stations. So in summary, so radionuclide anomalies are complicated because you have changing weather, you can have changing emissions, and you can have a low signal injected in all of that. Currently, abnormal thresholds are calculated based on univariate statistics or quantiles. A machine learning algorithm like the one I demonstrated here can extend that to multiple dimensions and help speed up the identification of collections of interest. And with that, I think I've got a little bit of time for questions.
Thanks a lot, Dan, for a really interesting talk. Okay, so questions? I see one there. Do we have a microphone? How does it work?
Yeah, thank you. Thank you. Very. Do you hear me? Yeah. Thank you. Very interesting. I think that's quite nice to see the machine learning there. I have just one question. If you compare it to the current quantile approach, how does it perform? That's one question. And the other question is, can you give an idea on the false positive rate and true positive rate, for instance, using machine learning compared to quantile, for instance?
Yeah, those are very, very important questions. So like with any algorithm, you might have to calibrate it. So here we get scores, but those need to be calibrated to traditional quantile scores. And then you would go in and assign a false positive, false negative rate. I have not done that for the data that I just presented, but that's sort of the next step, is to do a calibration on that and then see how well it performs. I expect it to perform comparably for a univariate sort of sequence. Doing a bivariate or higher dimensional quantiles, those are a little bit trickier. So I'm still thinking about the steps to sort of do that comparison.
Okay. More questions? Yes, Martin.
Thank you for your very nice talk. So you showed two different packages there. Did you compare the results from these two packages? Did you have the chance to compare them, see which one is more efficient, which one is more reliable?
That's also a very good question. I have for many, many years been using the sklearn package for much of my work, and so I'm more inclined to jump in, and that's what I used for the results I presented. The other package, I wanted to find out what else is out there, and I have not yet explored that, but I was pleased to see that it offers a wider selection. It specializes specifically in anomaly detection, and I have not yet tested that. But that's also another thing on the item of things to do.
Thank you.
Thank you, Don. Very good presentation, and anomalies are very important to look for. Your method seems, or your studies are very interesting. I just worry that a nuclear test signal may not be an anomaly. It may just hide among the data that look like normal observations. How do you deal with this? Can you study the kind of metric of performance with this regard?
Yeah, that is. So it's the, there's a true negative it's a negative, it's a positive signal that doesn't, so it's the false positive that we're worried about. And I think doing some calibration might help, but these are working by the magnitude, and if the magnitude of the signal is comparable to the background, then I think we're required to bring in additional information. So if there's seismic information, then that can help constrain some timing on when we might expect a collection. So then I think we would dial in a bit more and focus in on a subset of points to see if we see any slight elevations or any interesting anomalies with respect to ratios and other types of data. And
any more? I have one.
Oh, okay.
Yes, you alluded to this already, but actually if you compare the magnitudes in a multidimensional space, that's the same as looking at ratios, isn't it? In a way.
Yes, in a way.
So then if one could find a way to compare with hypothetical calculations in that space, it would be, you have everything together, both magnitude and ratios, actually. So, what do you think?
Well, what could be interesting, so when you take a ratio, there could be an anomaly in the numerator or denominator that's separate from the ratio. And if you're only looking at the ratio alone, you would miss that. And so by looking at the isotopes individually, you can see something interesting show up in one but not the other. But then if you bring in the ratio as well as a constraint, you could include that as an extra component. So, but I'm looking at this as maybe a vehicle for also bringing in not just different isotopes, but ATM data or correlations across stations. And that would be harder to, I think, to assess with, a ratio alone.
Okay. Right. Thank you. Okay, so thank you very much, Don. Thank you again. And we go on with Ian Hoffman, talking about reconstruction of synthetic radionuclide source terms using Bayesian inference. Please, Ian.
Thank you. I guess I should have prepared my own joke.
Yeah.
All right. Yes. Good afternoon, everyone. This is my talk on the reconstruction of synthetic radionuclide source terms using Bayesian inference. For those of you who've been around for a little while, this was done using a software program that we call Freer. And I'm going to show you a little bit how this worked on a blind trial with multiple participants and using Freer. So this is just a quick outline of my talk. I'm not going to go over this in any detail because we don't have a lot of time, but you can just kind of see what we're going to be talking about here. Basically, there was two different trials that we did. One was a long-range trial, kind of on a sort of continental type scale, which would be more like a CTBT type application, and one is a short-range trial, and then I'll show you some results and conclusions from this. So, verification in CTBT often involves information from multiple technologies, and they have an inherent problem of time scales where some information comes in very timely, like the seismic and the waveform information, and they can give you very good location information, but in contrast, radionuclide information can arrive sometimes even months later, like it did in DPRK 2013. The nice thing about the radionuclide information is it gives you the chance to confirm a nature of an event, but we're trying to see if we can do any better with location and timing. And early on, there was this concept of a possible source region, and you can see it's not an actual possible source region here. This is just a field of regard, but this is kind of what happens when you look at events over a long period of time, is that you end up looking at something that could have come from anywhere in the continent, and we're trying to see if we can do something better. So Freer was a tool that we developed using Bayesian inference to do, hopefully, a more informative and better job of what the PSR is showing there. So, again, this is what we're trying to do. We can shrink the geographical footprint under consideration using Bayesian inference. We can also provide uncertainty estimates in any of the parameters that we infer. This is something that isn't possible with the PSR type approach. And we can determine the release period and size of release very directly from the data. And we can incorporate a source term profile, so it doesn't have to be a particular hypothesis beyond the source term. You can put in your own. And it has an accurate model of how the detector behaves, and statistically this would be called the left sensor detector, where there is a measurement floor below which you cannot say that there was no signal or some signal. So how well does it work? This was what we were trying to test. And I said we did a short range and a long range scenario. We had one organization, AFTAC in the United States, generate two case studies for us. They used Whorf high split in a fictitious radionuclide network, and 3 different organizations performed their own independent reconstructions. And this ended up involving different meteorological models, different dispersion codes, and then just different choices in how you do your reconstruction. And this is kind of what we were looking at to see how robust FREER was and what we could say about working in this with these different models. So this is what I have here on the slide is the 2 networks. On the right-hand side, you can see the short-range network. This is what I said was similar to an emergency response kind of scale. On the left, you see the network for a longer range mesoscale, which is kind of closer to the IMS network. And so the data that we got from this trial, in the long-range case, there was 10 detections and 100 non-detects in the period that we were looking at. We were basically just given a time frame, and we had to kind of decide what our priors were for this. And in the short range, it was 10 detects and 38 non-detects. So this was a bit of an information-rich scenario than what we are often faced with, but this was something that we wanted to try and see how well this tool was working. And in any of these cases, we're trying to just answer these questions. Where did it come from? When was it released? How much? And how long was the release period? So to start off, we looked at the long-range trial because that was closest to the CTBT. So FREER, it's a Bayesian inference tool. We set our priors in there, which is our hypothesis as to where things are and how big they were. So we put in the spatiotemporal domain that we want to look at. We put in size bounds on the release. We pick a source term profile if we want. And then we have to decide what our input dispersion model resolution is, which is kind of external to FREER. And what measurements do we want to include? Do we want to put them all in there? Or do we want to select some and be a bit choosy about what we put into the reconstruction? And then we have to put in an uncertainty term for the source receptor sensitivity. Or we need a source of uncertainty in the atmospheric transport modeling. In this case, we had to use our own estimate of uncertainty in a deterministic way because we didn't have an ensemble. And so FREER then does Markov chain Monte Carlo sampling of the high dimensional solution space, and it's using an algorithm called MT-DREAM-ZS. So now I'm basically just running through a bunch of results. So this is the long-range results here for Health Canada. This was done using MLDP, which is the model that Environment Canada uses. It's a coupled model, so it involves both the dispersion and the meteorological model all in one package. And you can see at the top, this is in British Columbia actually, near the border with the Yukon. That's where the source was, and the predicted location. And then on the left side, you can see all the parameters that were being inferred. And I apologize that this is a bit small, but what this means is we have a good estimate of the longitude. We have the size within a half order of magnitude on the release, and we were able to really estimate the release period. And the true result there are those red bars, and the dashed blue line is the posterior estimate out of FREER. So we were able to get a fairly good reconstruction of the source. You can see that the most probable location, though, is still a bit south of where the actual source was. SCK also participated in this, and they were using ECMWF and FlexPart. And you can see a slightly different graphical display, but you can see that they basically got a very good reconstruction as well. However, their reconstruction extended a bit too far into the east. And one of the nice things about FREER is there is a posterior estimate of the model concentration that you can actually compare with the actual samples. And that gives you a bit of information about how well your reconstruction is doing, what you might want to include in the reconstruction, and whether or not you may have a problem with what you've kind of set up. The last organization that participated in this was AWE in the UK. They used NCEP with the Global Forecasting System, GFS, and high split, and they actually probably had the closest reconstruction overall. You can see that theirs was fairly well located, and they had one data point in the posterior prediction that was a little bit off, and we were trying to understand a bit about how this was behaving in the model. So great. I think we had fairly good results there. We looked then at a short-term one and wanted to see how that behaved. And this is a quite smaller scale. And it's not something that we had looked at really too much at all with this case before. So I'll show you just quickly the results here as well. This is the short-range results. You can see the source at the star there, and in the posterior prediction out of Freer. There was a good overlap here. And again, we got a good reconstruction overall using just the 3 largest observations in non-detects. So in this case, we did do a bit of sampling about what we wanted to include in the reconstruction, because the 3 largest observations were an order of magnitude larger than all the other observations. And I will just point out there is a bit of a mismatch in the stop time of the release there at the bottom, and it doesn't look too good to begin with until you ask the question about what the actual source term profile was. And in this case, 98% of the release happened around the time that we reconstructed it. So the stopping part, where the red line is about the 2% of the source that was actually released there. So you can see that Freer actually did do a very good reconstruction because of the way the source profile was done with its exponential tail. SCK also did similar results as well. Again, slightly different graphical display, but they had a very good reconstruction. And AWE did the same thing as well, and they also had a very good reconstruction. The red box and the right just being the domain of the sampler network, and the heat map just to the left of it showing the results. So I would say, or argue at least, the trial was generally successful. Freer was able to estimate the source parameters, and it was more informative than just using a PSR or a field of regard. It does make decisions easier regarding the nature of events. There is some evidence that if you want to do these reconstructions, you might need to carefully select the data to get the best results. And we did kind of observe with the AWE reconstructions kind of qualitatively that because they were using the similar weather prediction and dispersion model as the source, the synthetic source scenario that was generated by AFTAC, they seemed to get a better result out at the end. So to kind of evaluate this in a more quantitative way, we might need to look at doing ensembles. That may actually get you a more accurate representation of how the code is actually working, to compare when you're not using the same meteorology in the forward mode as the backward mode. And that is the end of my talk.
Thank you very much, Ian. So we have time for a couple of questions. Yep.
So,
You can wait for the microphone.
Yeah.
the synthetic data was constructed using WRF, GFS, and high speed, right?
Yeah.
And the AWE model was also similar.
Similar, right?
So the difference is like why it couldn't predict more accurately, because the priors were different, or?
So the scenario was generated using WRF and high split. So it is, the underlying meteorology is slightly different. I'm not sure that I can answer the question about how different that would be, though, than running with NCEP GFS. That's the same meteorology, but I'm not quite sure how that nests into WRF. I think WRF ran with a different nested type domain construction. We didn't actually get into a comparison of how that was generated.
Thank you, Ian. My question related to uncertainty in concentration value in modeled on observations, because in Bayesian inference, it is very sensitive to sigma, the standard deviation value of this. So how can Fourier deal with uncertainty in modeled and observed concentrations? It's observed concentration already, it's given, you can know the uncertainty, but what about the model uncertainty? Thank you.
So I think if I understand your question correctly, you're asking about the error bars on the posterior predicted amounts?
In Bayesian, we calculate the difference between observed, cost function, observed minus modeled over the standard deviation of both standard deviation of concentration, modeled and observed. So an accurate value of this standard deviation give totally different solution. So you should be care about this sigma. That is my question. So how Fourier did with sigma in Bayesian?
Okay.
Okay, that's my question. Thank you.
I think I don't have a precise answer to that. I can tell you, at least as far as I think all the participants were concerned in here, they all used 300% uncertainty in the atmospheric transport modeling. And that was what was used as far as the spread for what we thought the atmospheric transport modeling uncertainty was. Pieter has a comment, I guess.
Last question.
Okay, thank you for your work. Maybe the most thing in the Bayes method is the function of the likelihood. Have you compared the results of fair function with other functions? Not just one example, but a lot of examples.
No, we have not. We've only looked at one likelihood function for Fourier. That's it.
Okay. All right. I think we should move on. All right. Okay. One last.
Just a very brief question. You talked about the importance of sample selection. So how was this done? Because I mean, this was also a topic at the open intercomparison exercise I led, that finding the correct samples, or the most appropriate samples, has a huge influence on the results.
So that's a great question. In fact, that's a follow-up project that I want to look at for this tool, is looking at heuristics for deciding on some of these things. I showed you one result where we looked at the three largest samples because they were all an order of magnitude larger than the other observations. Sometimes that gives you a better reconstruction than just putting everything in there. But some of these things you can get a very good kind of initial guess or an initial result, and then you can kind of refine them as they go. And the overall reconstruction is still, seems to be fairly good, but you can improve it slightly by doing some sample selection.
Okay. Right. Thank you very much. Okay. So that question was very good because it takes us to the next talk, which is Harry Miley, talking about the development of an association algorithm for radionuclide measurements. Please, Harry.
Hi there. It's a pleasure to talk to you today, and I can see myself, and this is totally not going to work. I'm just going to stare at myself. So hopefully you all will be seeing my slides here shortly. Right? Okay, great. So about my talk. I had an idea for a talk, which I pitched to my colleague, who wrote a talk, and then he was told he couldn't come, too many people, and so the talk was pitched to another person who rewrote it, and then unfortunately he couldn't attend because he's ill. And so now I'm seeing this talk, and it's not exactly a talk that I would normally present. It has words and things in it, so I'll do my best. But it is meant to exactly follow on after Ian's presentation. We asked the question, yeah, it would be good to see them. We asked the question, we have a Bayesian tool, and I think other research organizations have a Bayesian tool, but Fourier kind of got a lot of visibility and attention. So we asked, does it have a scheme in which it selects associated samples objectively in order to feed into Fourier? And the answer was at least not yet. So we spent a pleasant Friday afternoon trying to think of a way to create an association algorithm, and found that we already had most of the ingredients that were necessary. And I refer to these Bayesian calculations as Yeah, that looked like it, actually. I can talk to any of them. Just run some slides. That's fine. We determined that a lot of calculations we had done, if you remember, Ted, a few years ago, you asked us to do some sort of study, and also Lee, study related to backgrounds or something like that. And we did a lot of computations associated with that. Next, please. Or can I run it? Okay, you've seen the whole talk now, so let's see. So we found that the computations we had already done would support the creation of a humble association tool. And after we're learning to use each other's languages, after years of conversations from a seismic colleague, is Yochai here? After years of Yochai patiently explaining how global association worked in the seismic world, we thought we could create something that was some sort of a beginning. So we're not making a claim that that we have the final solution. Somebody here can create that. But we do have a vision for what a next generation pipeline might look like. So if you look at the blue boxes at the top, there's an IMS system. That's the systems that have a specific sensitivity and selectivity out in the world. And they produce a spectrum. And the spectrum that you see there happens to be, I think, the first xenon spectrum that Ted ever took in New York City many, many years ago. Then you go into some kind of a flagging system, which is the sort of anomaly system that we created many, many years ago for level 5 or level C, depending on if you're particulate or xenon. So this is all this IDC anomaly detection that we're crunching down into the first box called detect anomaly. We have a lot more ideas. They're not ready for prime time yet, but we are working on some fresh ideas for anomalies. And so, of course, love to see Don's talk about that. Then the sample associator, which is the purpose of this talk, would then feed a list of samples to your Bayesian tool. I've referred to this as a Bayesian soup, where you put in your measurements and you get out estimates of T0, the release strength and location, just as Ian just showed. And that this could generate a first level bulletin, and after analyst review, because we're all in love with large language models and things like that right now. They're very fascinating, but they can make, the computer can make the mistake it would take thousands of years for a human to make. So a subject matter expert is going to be in the loop or on the loop for the foreseeable future. After analyst review, then you'd have a final event bulletin. And these kinds of tools could eventually lead to waveform fusion. So we're very excited that the radionuclide community is catching up to this kind of pipeline calculation. So I've said enough about that, but today we're talking about sample association, and we're also here, I am, and also hearing in this session about the other boxes. Okay, finally, we can go on. Oh, and I can do it, can't I? Maybe. All right, so what is sample association? Now, if you're from Washington State and you look at this, you might recognize all the folks in the room from Pacific Northwest National Laboratory. Their offices are right under where it says detectable plume. And there's a Hanford reactor that's right underneath the explosive. So we used a local map. So welcome to Eastern Washington. If you had a release at this location and the red thing is the plume coming downwind, detectors 3 and 4 are in the plume and would, according to my cartoon, get a hit. 1, 2, 5, and 6 would not. But the sample measurements that occurred at 2 and 5 could very greatly help confine the location that the source was. So that's the logic. Which are the right samples? And when I created this slide, the number 5 was in the upper right-hand corner, and at this point I would say 5 is right out, and that's a Monty Python reference, having to do with a hand grenade. Sorry people. Okay, that was the whole reason for that slide, to be honest. But So our summary is that we have a first level automated association approach, and it's objective, but there's still questions about how you might use it. The last time I gave this talk, and I'm not an atmospheric scientist, and I probably said some of the wrong words, but we used a full year of data. And you know, the winds blow in different directions all year and so forth, and we did it for the entire Earth. And so it was kind of called climatological because it was using average over a long period, I guess. But we also have the idea that if you were in spring of 22, you might look back just at the previous springs. Or maybe you just look at the previous 2 weeks. None of these approaches imply a greater or lesser amount of computations. They're all about the same. It's just a question of what you get out of it. And the approach, I might not have even had this slide. How did we do it? You know, just making funny hand signals. We took 79 stations and picked 100,000 locations on the globe and made a synthetic release for every 3-hour period over that year in 2014. And then we built a huge matrix of detect and non-detects, and then looked for, if, for instance, I had a detection at Takasaki, did I also have a detection for these hypothetical events at Usurisk and Okinawa and Beijing, et cetera, et cetera. So then we would build up a value for, if you were interested in Takasaki, how valuable are the surrounding stations? And it could be over the last 2 weeks, or it could have been over the last year. So here's an example, which we took for the important reason that it was number 1 in the list, Argentina. And this depends on how large the release is. That's an important caveat. So for a 10 to the 15th becquerel release, it doesn't really even matter if it's a becquerel or a Curie, just a 10 to the 15th release. The station at 4,000 kilometers appears to have the greatest affinity at about 0.65. In other words, 65% of other detections, 65% of the time, that station would also see what Argentina saw, which is fantastic. But if you have a smaller release, then the stations that are much closer are important. So for smaller releases, you see that the affinities peak out at about 0.2, not nearly as high. So we'll look at a concrete example here, and it's the example that I roll out just about every time for every purpose. DPRK 2013. So we actually had 3 detects and any number of non-detects. But if we only put in 1 detect, we would have this potential source region. And these are in probabilities, not dilution factors, probabilities of location. What I'm not showing, to be honest, is that there's up to the upper left, I guess to the northwest, there would be another big region that was green and purple that we couldn't tell the difference between. So we couldn't define that. But by adding in a second sample and, adding in a non-detect, just 1 non-detect, we eliminated 1 large lobe of probability of the pink part. That's the high probability part. Adding in 2 detects only, no non-detects, it's further constrained. By the time we get to 3 detects and 2 non-detects, we have a very tight location. So this is the value, I think, I'm just adding to the things that Ian was saying. This is the value of collecting up a number of detects to make a location. But what really the point of this slide is that if you look at the high affinity things, for Takasaki, you see there's Usurisk, Okinawa, Petropavlovsk, and Beijing, and the affinities are dropping away radically. Those are literally the stations we would look at. A human analyst would say, tell me what's going on in Usurisk. I want to know what's going on in Okinawa in order to make a decision. So the computation is handing us back what a human would do, but it's doing it objectively and presumably overnight. So when the analyst comes in to look at this radionuclide event we've created, it's already fairly reasonable. And they can toss it out if not. I probably would not have shown this slide. It's a little bit complex. This is showing some of the raw data that's in the affinity calculation. And so the question here is, if Ashland, Kansas, that's in the center of North America, is that RN 74, had a detect, but Charlottesville, Virginia, RN 75, did not. What are the, I don't want to say possible source region, because that term is already taken. But what are the places with high affinity? Well, it would be like Western US or maybe a bit of Western Canada and out at sea. But it would not be anywhere close to Charlottesville, Virginia. So it kind of makes sense. So another thing is that if you were trying to interpret data, you could just query the affinity calculation and say, in the past, how has this looked? To give you a little more confidence. And here's yet another example. This is an example where we hypothetically have a detect at RN38, Takasaki again, but not in Beijing or Usarisk, that is RN20 or RN58. Okay, we'll wrap this up. The point is here that this kind of probabilistically builds a wall between RN58 and RN20, and it's very difficult for any source to have been upwind to the northwest of that location. So these are examples of things we can just directly use the affinity calculations for. So in conclusion, we constructed a basic sample association scheme that's objective, and it returns results that are similar to what a human would pick, but overnight when the human's asleep, I hope, and uses averaged historical air movement. Once developed, this affinity matrix just becomes a lookup table. And we think that this initial sample association is just a launching point for analyst review. Some people think you're trying to get rid of the analyst. Can't do it, because this can also return ridiculous results. Okay, and with that, I'm happy to take questions under the chairman. Thank you.
Thank you very much, Harry. So, questions in the audience? Yes, there.
I'm hoping to not get questions of the caliber that were given to Ian.
I'll do my best.
Okay.
Nice talk. So I was just wondering, you mentioned at the beginning that you could build your climatology from, X number of years, or you could do this previous springs. Does that make any difference to your results?
It should. You should expect that we've noticed that there are seasonal direction winds just looking at that region of the world, which we've looked at quite a bit for some reason, that there are some directionalities that are preferred. So depending on the time of year, Okinawa would not be likely as a second detect to go with Takasaki, but Usarisk would, for instance. So yes.
Thank you.
Thank you for not asking questions. Oh, wait, there's one of my colleagues that's going to ask.
So, Harry, I probably just missed it, but in the affinity calculations, it seems like there's going to be time offsets for the different stations. Is that all built into the meteorological aspect of the calculation?
Absolutely. And it's also built into, as I understand it, Freer and other Bayesian codes are happy to work with differing time periods, unaligned time periods, and so forth. That should all work fine.
Okay. Thanks again. So let's go to our next speaker, which is Pieter de Meutter, talking about a baseline for source reconstruction using forensic radionuclide event analysis and reconstruction. Please, Pieter.
Thank you. Oh, I thought we started with questions, but here is the presentation. Great. So, here is the content of my talk, and there is nothing too uncommon. So let me just go to the first slide, which gives some context to this talk. So inverse modeling allows a determination of the source parameters of a radioactive atmospheric release by combining atmospheric transport modeling and airborne radionuclide measurements in a statistically coherent manner. And it boils down to the following equation, where you have the vector of radionuclide observations, which is approximately equal to the source receptor sensitivities obtained by your atmospheric transport model, and then a vector containing the geotemporal release data. And so inverse modeling enhances 3D verification as a technique to link radionuclide detections to a potential source. And here what we did is we conducted a series of inverse modeling experiments using Xenon 133 observations associated with the former medical isotope production facility at Chalk River Laboratories. And the purpose is to establish a baseline for source reconstruction in order to test data, methods, and settings. And we used Xenon observations at 4 IMS stations, and you can see the location of these stations on the figure on the left-hand side. And we took observations from the 1st of September until the 30th of December 2014. So we had 120 days of observations, and here is a little recipe to make the Bayesian soup that was mentioned by Harry. So what we did is we divided this period of 120 days into either 8 cases with 15 days of observations, and also in 24 cases containing 5 days of observations. And then we performed inverse modeling on each of these cases separately. So we consider them independently as a case study. You can see on the right-hand side the time series of the 4 IMS stations, but I will not go into detail. And so the aim was to reconstruct the source location at this point, so only the source location of Chalk River Laboratories for these either 8 cases or these 24 cases. For that, we used the Bayesian inference tool FREER. And this has now 4 methods implemented. So there is the Bayesian inference approach, a cost function optimization approach, a maximum in time PSR using the Pearson correlation, but also the Spearman's rank correlation can be used. And finally, there is also the accumulated in time fields of regard. And these methods go from, let's say, more elaborated to a more simple approach, because in the first 2 methods you use information such as the observations, the atmospheric transport modeling, and a certain source parameterization, so the y, the m, and the x, while in the PSR method you only use the y and the m, and then for the fields of regard you only use the m. So the method becomes inherently less complex. And for the first 2 methods, we've used our own ATM simulation, so the ATM experts can get the details on the slide, but I will not discuss them. I'll just mention that we've used daily FlexPact output, which is a bit uncommon, but we think that it is sufficient in general for our application. And for the other 2 methods, we have used the source receptor matrix that was calculated by CTBTO. And then in order to facilitate the analysis, we define 3 verification metrics for the source location. And the first metric was the distance between the most likely source obtained from our inverse modeling to the true source location. And the best value, of course, is 0. Now, what you can see, this colored field, it represents, for instance, the source location probability in case of Bayesian inference, or minus the residual cost in case of the cost function optimization approach. And so if you take the distance between the maximum and then the true source location, you get the first verification metric. The second metric that we've defined was to simply take the quantile at the true source location. So ideally it should be 1 if it coincides with the maximum source location probability or the minimum cost. And then the third metric is the fraction of domain that can be excluded by the inverse modeling. And ideally, it should be as close as possible to 1, but contrary to what the slide says, it should not be 1, because then you don't have any source. In order to calculate this fraction of domain that can be excluded, we have defined a few thresholds. So they are shown here on the slide, and these are based on expert judgment. And okay, you can get perhaps slightly different results depending on the choices that you make here. Here you can see an example for one case where we have used 15 days of observation. And you can see the 5 different methods that I've just discussed, and also the 3 verification metrics. So at top left, you have the Bayesian inference approach, where you can see a very small region close to Chalk River Laboratories. So this was a very successful reconstruction. Next, you have the cost function approach, which also does a good job. Then you have the maximum in time possible source region using the Pearson correlation. And next, in the bottom left corner, you have the same PSR, but then for the Spearman's rank correlation. And then lastly, you have the fraction of overlapping SRS fields associated with detections. So when we look at the distance score, we see that the Bayesian method does a very good job, but also the cost function and the PSR using the Pearson correlation does a good job, while the other methods are a bit further off. The quantiles are generally high, not for the Bayesian approach, because if you look carefully, you will see that this source location probability just touches Chalk River laboratories, and it does not include it. And this should be investigated further. I just want to highlight that the Bayesian method is the only one who infers the source location, while the other methods are applied for each grid box. So there is some inherently difference there. Let me go back. Yeah, and then finally, if we look at the fraction of domain that can be excluded, this is very high for the Bayesian approach and the cost function approach, but not so high for the other three methods. Okay, and then as a first test, we compare the 5-day set of observations with the 15 days of observations. And you can see here results for the three verification metrics, so distance, quantile at true location, and then the fraction of domain excluded. And I don't know, does it point? No, there was no pointer, I guess. No. Okay, and you can see each of the 5 methods on the x-axis. So we have first the Bayesian approach, then the cost function, the PSR using Pearson, the PSR using Spearman, and then the accumulated fields of regard. And in red, you have the 15 days, and in green, the results using only 5 days of observation. And so a first conclusion is that more observations obviously allow for improved source localization. So there is a significant decrease in the distance score, which goes from a median of 800 kilometers to slightly below 300 kilometers for the Bayesian inference and the cost function approach. There is also a significant increase in the domain, or the fraction of domain that you can exclude as a likely source location. And then third, for the PSR methods, there was only or a smaller reduction can be seen in the distance score, and actually a deterioration in the fraction of domain excluded. Next, I want to briefly highlight the effect of the source parameterization, and this was applied to the cases where we had 5 days of observation. So I consider either a constant release or 2 5-day release segments, 5 2-day release segments, and 10 daily release segments. You can see the results here. And I'll just briefly touch on a few observations. So first of all, the source term parameterization can have an important impact on your source reconstruction, because if we compare the first 2 results for the Bayesian approach, we can see nearly a factor 2 difference in the distance score, so this is significant. And secondly, if you add extra degrees of freedom to the source parameterization, it will generally result in a better reconstruction of the source, but also it will make the problem more ill-poised. And this can be seen because the fraction of domain that you can exclude decreases by increasing more degrees of freedom, which is what you expect. Then we did also, I would say, a naive selection of observations, naive compared to the more elaborate methods that other colleagues conduct. So we apply this here on the slide on the 5 days of observation, and we either use all observations or detections only, high detections only, so meaning observations above 1 millibecquerel per cubic meter, and then we combined non-detections and high detections only. You can see the results here, so I will guide you again through the figure. So in general, if we include non-detections, we get a better source localization. And then specifically for the Bayesian inference, if we use the non-detections and high detections only, we get the best results. Now I show here the same, but for the cases where we use 15 days of observations. And then we see a bit similar to the previous slide, but more pronounced, that the Bayesian inference significantly deteriorates when we use the detections only. And this is also true in some sense for the cost function if you look at the quantile at the true source location. Another observation is that the cost function method is less sensitive to the non-detections and small detections, but this is by design of the cost function. So you can see here that the distance score is fairly robust, let's say. And then the last result that I'd like to show is testing a new cost function. So we've defined another cost function that we think is slightly more sound compared to the original one. And I'll not go into details, but we think this is slightly more sound. And now the question is, does it also perform slightly better on our test cases? And this is now quite easy to test because we have this set of case studies. And we see here that the results of the new cost function on the scores is either neutral or it results in a small improvement. And from this, we feel confident to indeed implement this new cost function in Freer. So I have a set of conclusions, but I'll just show them on the screen. I just want to say that these sets allow to compare data such as observation selection, NWP input, ATM input. We can compare methods, inverse modeling methods, source parameterizations. We can test new developments on inverse modeling, and I think this is just the start of the analysis on this data set. And yeah, I look forward to do more research on it. Thank you for your attention.
Thank you, Pieter. Really nice to see a comparison between the different localization techniques. I think that's really good. Please, questions?
Thank you, Pieter, for this interesting presentation. I have two points. One related to the cost function. I don't see it well, but the Gaussian cost function exponential like this, it's have a physical meaning. It's give likelihood, probability. So I'm not sure about your equation. So we can interpret it as a probability or likelihood. Or there is another point related to using detection, non-detection. So you showed that using both as very powerful. So we missing in the field in what's web grip. We only use detection. So I think one of recommendation of your presentation is that it's important to include detection, non-detection both in web grip, so it can improve, as you show, improve the possible search detection. So thank you.
Mm-hmm. Yeah, thank you. So regarding your question, for the Bayesian approach, indeed we have a likelihood based on the Gaussian probability, and then the interpretation is also can be probabilistic. For the cost function method, we don't use a Gaussian cost function. We use the geometric variance, which we found was performing well, but as a consequence, we can't interpret it as a probability. Yeah, also the new cost function is also based on geometric variances. So yeah, it's not interpretable as a probability. Yeah. Okay, thank you.
So let's move on to our last speaker for this session. And it's Emily Gordon going to speak about performance evaluation of Radioxenon isotopic ratio flags and possible optimizations. Please, Emily.
Good afternoon, everyone. My name is Emily Gordon. I'm from the University of Texas at Austin, and today I'm going to talk about a recent performance evaluation of Radioxenon isotopic ratio flags and some possible optimizations. As many of you will be familiar with, the chart on the right is a multi-isotope ratio chart, which shows the activities of 4 different radioxenon isotopes. And it can be separated into a reactor domain and a test domain using the red screening line for a threshold. The problem here is the data can only be put on this chart if all 4 isotopes have been detected in a sample, although often only 2 are detected at a time. A simplified approach would be to use only 2 isotopic activities to calculate ratios, as shown by the 2 green lines on the chart. The figure on the left is an example of a radionuclide report, which shows the results of 3 radioxenon isotopic ratios, which are currently implemented for the IMS and their current threshold values. The problem currently is that these screening flags are hardly ever showing yes. So the idea of this project was to look at, could we make the ratio thresholds more effective? What would be the best method for calculating the ratios? And could we add an additional radioxenon isotopic ratio to the list of screening flags? When considering the screening flags and the ratios related to them, we don't look at only what is the calculated ratio of the radioxenon isotopic activities, but also what are the bounds of the confidence interval. So if a ratio needs to be above a certain screening line to be considered suspicious, not only does that value need to be above the screening line, but also the lower boundary of the confidence interval. So the current method for calculating the lower bound of that interval is Bayesian analysis. We also considered an additional alternative method, a geometric approach to finding the confidence region, which uses the slope of a line that would pass through the intercept and then run tangentially to the error ellipse. So we're considering 2 different calculation methods, Bayesian method and Field's theorem, 2 different confidence intervals related to both of those, a 1 sigma and a 2 sigma. And additionally, we also added a 0 sigma confidence interval, which would basically just be ignoring the concentration uncertainty and only looking at the value of the ratio itself. We applied these calculation methods and confidence intervals to a data set comprising over 35,000 IMS samples from the stations listed there between August 2012 and August 2016. After we had calculated the ratios for all of these IMS samples, we then sorted each of those resulting columns of data and then placed new threshold values at 1, 5, and 10% false positive rates. After we came up with these new threshold values, we wanted to score them, and we did so by adding together hypothetical signatures with actual observed xenon concentrations. So we started by choosing samples from JPX38, which represented all seasons, and we chose dates where both isotopes of the relevant ratio were present above MDC. Using atmospheric transport modeling, we found a transport time and a dilution factor from the DPRK test site to RN38 in Takasaki, and then combined the actual observed xenon isotopic activity concentration with hypothetical nuclear explosion signature using the dilution factor and the transport time. When we were considering adding the actual observed activity with the hypothetical signature, we also need to predict what the uncertainty in that concentration will be so that we can find the upper and lower bounds of the confidence interval. We did this by looking at going back to that data set of 35,000 IMS samples and fitting a generic function for uncertainty in the activity concentration so that we could predict what the concentration uncertainty would be for each of the isotopes. These are results of the first part of the study, which was to set the new possible threshold values. So we only considered samples where both isotopes were present above the MDC, and that resulted in between 1,300 and 1,700 samples being applicable depending on the ratio. The numbers in red under Bayesian 2 sigma indicate the thresholds that are currently used in IDC operations. So you'll note that for the 3 radioxenon isotopic ratios that are currently in operation, All of the newly calculated threshold values are below the currently in operation values. This is the results of the second part of the test, which was to score the threshold values using hypothetical signatures. So combining the real and hypothetical signatures, we compared those resulting ratios with the calculated screening flag thresholds. Each of the calculation methods was scored by tallying the number of detections, so how often the sample would result in a screening flag being raised. Because we used 6 samples for each ratio and 24 different released activity combinations, the highest possible score would be 144. You'll notice that the results were not consistent across the different radioxenon ratios. For example, for xenon 131M to 133, the highest score was 72 using the geometric Feeler's theorem approach with a 2 sigma confidence interval. However, the same approach for xenon 135 and 133 and xenon 133 and 133 all had 0 detections. So in conclusion, we calculated new screening flag thresholds for 4 radioxenon ratios, including one that is not currently in use by the IDC operations. We looked at 2 different methods for interpreting the confidence region, Bayesian method and the geometric approach, or Feeler's theorem, and we compared these approaches over 3 uncertainty intervals and 3 false positive rates. Our results showed that no combination of calculation method and uncertainty interval were universally superior. It depends on both the radioxenon ratio and the false positive rate. So in the future, we would like to refine the method for predicting activity concentration uncertainty, and more importantly, to expand the number of test cases so that we can get a more detailed information about the results of the hypothetical signature tests. Thank you for your attention. I'd be happy to take questions.
Thank you very much.
Hey, Emily, great talk. It's super useful. These flags are going to be needed, as you mentioned. We're not detecting 4 isotopes much. I've seen through the years a disturbing, let's say, misuse of ratios when the uncertainties are not used. And so I was wondering about whether there was thought put into the uncertainties in the ratios for these flags and how that might be incorporated. Or maybe you already did it and I missed it.
Yeah, so we're definitely including the uncertainty in 4 out of 5 different approaches. We did also look at just calculating the ratio and just to see what those results would be. But yes, we are considering the uncertainty in the activity concentrations.
Thank you very much for interesting presentation. I have a short question about uncertainties of ratios, activity ratios. You have considered 2 approaches, Bayesian approaches, yes, and Feeler's theorem, yes?
Yes.
Yes, I have a question about other approaches, or only you consider only 2 approaches, and which of them is the best, or maybe 2 approaches is very similar, Bayesian and Feeler's theorems, and maybe there are some different approaches of calculate uncertainties of ratios. Thank you.
Yeah, sure. I'm sure there are different ways to consider the uncertainty in the activity concentrations when they're applied as a ratio. If you have specific suggestions, I would love to hear them.
Maybe I could fill in here. There is actually one method you can use the exact expression of the probability density function for a ratio as well. It's a complicated one, but I think you can solve it by numerical numerical integration, for instance. That's one possibility, for instance, I think. Okay, any more questions? Okay. If not, thanks again. And thank you very much to all the speakers for keeping the time and everything, and for a good session, I think. Thank you.
Thank you, Anders.